Oh, what's why?
Just the input system for it screwed me out of a couple points.
Yeah.
It's just getting re-adapted to format.
Yeah. Did it say like something specific in those small blue letters, or did it not say?
No, like the two ones that really stuck out to me was I typed in integer values that I had come up with, and it counted it wrong because I wanted the fractional version of it, even though what I put in the calculator was exactly the same.
Yeah.
And just lost a couple things there.
Okay. Yeah, you can always email me on stuff like that if you want.
I've got it written down. I just need to go back through my actual like scratch work.
Yeah.
Before I try to send it out.
Okay.
I have a hell of a time getting through it.
All right. Yeah, try to send me those issues with MML's syntax as you get them, right? I mean, I guess I can deal with 20 emails from 20 people at once, but I would rather them just come in as you notice them, if you have the time to do that. Would help me out a lot. Otherwise, not a big deal. All right, then we barely started 6.4. The hope is to get through 6.4 and 6.5 and to start 6.6. 6.5 and 6.6 are I don't know that they're like shorter sections, but as far as the amount of homework, they're much shorter than the other portions of Chapter 6. So they should go by fairly quickly. 6.5 and 6.6, that is. Okay, so we discussed the volume using the shell method. And our shells are 2 pi RH. And again, that could be with respect to x or with respect to y. In that case, with respect to y, it would just be 2 pi y. I don't know, let's call it g of y, dy. Or this here. Just really depends on what direction your cross sections are running. So remember our shells. When it says use the shell method, we want to draw our cross sections parallel to the axis of revolution. Unlike with our discs and washers, the disc and washers were perpendicular to the axis of revolution. So that's how I always remembered it. It's shell parallel. That's it. That's what I remembered. So shells are parallel to the axis of revolution. Okay, so let's look at an example. I think a lot of these will just set them up, and I can provide the answer if needed, but I hope at this point you're comfortable with like integration of certain things. There's not going to be any weird stuff you can't integrate. Maybe after Chapter 7, when we learn different like integration techniques, then we can start getting into more like elaborate type examples. But everything you see should be like antiderivative or use substitution stuff. So we have the region bound by cosine x squared. Remember, don't confuse cosine x squared with cosine squared x. Okay, so they're not the same thing. So just like with the discs and washers, I think the first thing we should do is, if we're not provided a figure, is to draw a figure. And then kind of orient ourselves as to what's going on. That's super, super helpful. So cosine of x squared, y equals to 0 here. And we're bound by the x value of 0 and the square root of pi over 2. So it's something like that. I mean, if on the exam, I think I would provide a graph like that. I don't think that's really a well-known function, as far as graphing. So, it looks something like this on this interval from 0 to pi over 2. I'll highlight this a little differently. It's the cosine of x squared. So again, they're saying the line y equals to 0, that function, and an x value of 0. Let me make sure I have that right. Yeah, and root pi over 2. So we're going to take that region, revolve it around the y-axis, and it says use the shell method. So just make sure that you're paying attention to the method that's specified. Shell method, we have that as 2 pi times the radius times the height. So we need the radius and the height in terms of x or y. We're using the shell method, rotating around the y-axis, so our shells are parallel to the axis of revolution. So those things have a tiny thickness dx. So everything in terms of x, we need our bounds, our function, we need r, the radius, and the height of each shell in terms of x as well. Okay. Is everybody good with that? Any questions or any issues setting these up? If you've done any of them? Just curious as to kind of what your experience of this is. Anytime I have a problem like this, I'll always draw this out. I always put my rectangle in there, label it, am I doing this with respect to x or y? I can literally do that every time. Okay, so we need to find the radius, and I don't know if I can illustrate this very well, but remember this is like, I'll exaggerate this, and we're rotating it about the y-axis. So that's like a cross section of the cylinder for that particular rectangle. Okay. So it's unlike the discs or the washers, the height is determined by this measurement here. This is the height of that rectangle. So the height of the rectangle is just measured by this length, top minus bottom, right? Which is just our function here. So h is the top minus the bottom, which is just equal to cosine of x squared. What is the radius then? X, do y'all agree? It's just some x value. Like if I'm here, the radius is that x value. Here, let me mark this here. That distance is the radius. That's what's getting revolved around here. That's just x. If you want to think about it as, you have to remember that it is some x value. But in some instances, depending on what we revolve around, we're measuring that dimension here, this length. So let's think about this as the x value x minus the x value here, which is 0. So when we're measuring that radius that way, it's the right minus the left, which is x minus 0, which is just x. And I think that'll be helpful when we start rotating these things around other axes. Like rotate this around the line y equals to 5 or x equals to -3. It's not a great picture, but I hope that kind of captures what's going on there. All right, then we just put it all together. The volume is 2 pi times the integral. Everything's in terms of x. So 2 pi times the radius times the height with respect to x. And our cross sections range from where to where in terms of x?
0 square root of.
Yeah, so they're running like this. So they're ranging from 0 to square root of pi over 2. Anyone have any questions on that? That was 0 to pi. Okay, so that's the setup. That's going to produce the volume using the shell method. Let me get this here. Oh, dude. I don't know if I can grab all that. No, it's good. All right, it stays. So how would we integrate that?
Would you use substitution?
Yeah. So what's tipping you off as that's a u substitution?
The x squared.
The x squared. So the x squared on the inside of the argument for the cosine of x. But remember the u substitution took the form, like our function was here and its derivative was here, or a constant multiple of its derivative. Sometimes we saw a little bit of deviation from that where we had to solve for our substitution. But since we have an x squared, its derivative 2x, constant multiple of its derivative, those are always u substitution. So we're going to let u equal to x squared. Everything's based off of your original substitution. So our original substitution, and then we take the derivative of both sides. So du is 2x dx. So we're really taking the derivative of u with respect to x, and then just multiplying both sides by dx to get the u's and the x's on the same side. Okay. So we only have 1 dx. So if you wanted to look at it like this, we can. We can also look at it. So that's usually, I think, I don't know how most people do it, I would assume. But if we looked at it and we said, well, I have a 2 times an x times a dx, here's a 2, here's the x, and here's the dx. So I could say that 2, that x, and that dx were all du if I wanted to. It's really a matter of preference, I think. Oh, geez. Anyhow, we're gonna, if we put the 1/2 in there, we see that it cancels with that 2, right? So either way, the 2's gone. We have pi times the integral from, or rather, cosine u du. So much simpler integrand, and I always recommend working with the u substitution with your bounds as well. You can find the antiderivative of that, resubstitute, and then plug in the original bound 0 to square root of pi over 2. Or we could just use the bounds for u, because as a reminder again, this is an x value, this is an x value. Here we want a u value and another u value. Okay. So if our lower limit, x equals 0, 0 squared is 0, so u is 0. Our upper limit, if x is square root of pi over 2 and we're squaring that, that just gives us pi over 2. So u is pi over 2. So that's much easier than what we're dealing with. I'm just curious, does anybody resubstitute and use the original bounds, or do you always change the bounds too?
I resubstitute.
Resubstitute, okay. Does anybody else do that? Okay. Okay, all right, yeah. It's perfectly fine. It's just, you inherently have a simpler integral to deal with your substitution. So that's the whole point of the substitution, was to make the original integral into something simpler, but It really is a matter of preference. All right. Running out of space, you should just get the answer as the volume rather, as pi. Do y'all have any questions on how we set that up? So naturally, you've got three different methods to find volumes of revolution. So I think it's super important, especially to stay up on homework like this, because things will just kind of start to bleed together if you do it all together. So if you have time this weekend, you might want to look at this stuff separately. All right then, I'll let you all try example 2.
So this
Okay.
and then when I resubstitute it, isn't it? Just that you integrate on it, but sine of u over
Oh, no. So just because we're integrating with respect to you, so that would just be,
yeah, that's, yeah. Wait, one, and it's just pi.
Yeah, so that's, okay, because it's asking you results. Because why I have this for you.
So why just be like the x-axis?
It's an angular volume around that.
So the X is this height, and the bottom is this. And then the side would be here, because they meet at the organ. So you got like this area here.
Which is why. That's how the distance from here. So why measure it?
Yeah.
The height though.
Which would be, would this be 4?
Well, it's it goes to the function.
Yeah. Oh, right.
Set.
I just included
X equals Y, set Y squared.
You guys ran.
It is
Fatal parallels. Yeah, exactly. So I just in terms of as far as
What did you get?
I got it. But you do it that way, that means that
I wonder if doing this with the other method, like other method, imagine if you just rotating.
It would be 4 minus 5 squared. But the answer is 2.
Same sheet.
So, what's happening? Maybe
That's
that
amazing.
cleans up an integral.
But I don't need us getting just.
Yeah, I mean, yours didn't like.
It's something I might do just
Y
y
times Y squared. Yeah, that's minus 4 squared. So it's minus 4.
It's just because it had to be square with a shell in there.
So you're saying like the region needs to touch the line and like your red or?
No, it's just like.
So that's like.
If it's revolving around something that's rotate around like maybe 5
What's your balance?
just set x is equal to y squared equal to. Although 0 is not like defined. Like it never says it get what's opposite. And x is what it does.
Oh. Okay. Oh, okay, wait. Okay, yeah. Okay, thank you.
Yeah, if the answer's on the board, if you, well, I lied. Some people are getting 8 pi, but they have the wrong setup.
Oh, there was nothing that like defined this. Is it just because like this one?
Yeah, it says bound by the square root, y equals to 0, and x equals to 4. So we're thinking like, what's common of all? Yeah.
0. Okay, and then question. So we're doing this. Yeah, but
I don't want to say that. Way off.
and then just take in terms of x and then rotate, which you can because they should be rotating the same thing.
We want our
Yeah,
dy.
so we're rotating this square around the x-axis. Yeah, and if you move the washer, because it is on same space. Yeah, I think we do.
So that's like the washer method. What you're wanting to do. The shell, you gotta like take watts. Or this is your
No, the shell is parallel.
This square.
yeah. So this is your so this is rotating on the x-axis.
On my side, the y squared revolves around
You had it right, just the wrong trail.
I was just confused by the one in front of, like, I redid this probably like 6 times.
Oh, that was a trick.
Like, one of them had an 18 and it was an 18 minus.
He got you.
Oh, yeah.
I just don't understand what that is.
X equals to
When you're doing
that one,
it
y
around
equals to
the
1 is here.
Who's top minus?
How far does the square root of the sine of x
It
go?
goes to 1.
It goes to
That's
1.
right.
Right? So then it continues this way, but notice that says find the region bound by the square root of sine. X equals to 0 and y equals to 1, so you're finding this area.
That's why.
And then volume.
Yeah, that makes way more sense why it's 1 minus now. Thanks.
You're welcome.
When I took
It should be y minus 6.
So like, okay, when you took calculus, you know, like there's, okay, when I took it, they have like, they have like,
There's always like, there's always
oh, okay, so it's just like,
and you'll never see them. That's just how it's always.
It's got to get better. Did you ask him about it? Apparently,
I didn't have time.
It's a confusing degree.
Then you get out. And the circle, that's where square root of x and x.
Trying to find that balance.
No, the top one, because all of the
When we start getting to all of the times before. Weekends aren't bad. I now feel that Keith will be rough. Yeah. It's like 10 my store having the same
should get to,
And then anytime I need a schedule change.
Yes.
that is 4 minus 1. That's 4 minus 1.
That's the mean. Yeah, that's the mean reason why like I don't.
And remember y is
Yeah, that's the main reason
multiplied
why
by the
I haven't
entire
tried to
4
find like a
minus
better
1.
way.
Flexibility.
Yeah, exactly. Make sure you have all this for this semester.
Remember, just remember that the y is multiplied by the entire of this.
But I was like, no, I need to have Mondays off. Because we need to do it. I can't start at homework. I can't just go into class with every single question. So I just
Okay, so make sure it's bound by, there's some weird ones in your homework. This one, hopefully, it's very straightforward as to what region we're revolving.
From 0 to 1.
Okay,
Y.
about the x-axis. Using our shells, it's parallel, so then, like, I don't know why some of these, if you set them up wrong, they still work. So I'll be looking for both on the exam. Do you have the right answer, which shows me you know how to integrate and plug in stuff? And do you have the correct setup, which shows me that you understand the concept? So the shells are parallel to the axis of revolution. These have thickness y direction dy. So anytime you draw, and I saw many of you that didn't draw the actual cross section. I think it's really helpful to draw that If you're going to draw a thick, rectangle, it's fine. If you're just going to draw a line, that's fine too. But then it gives you a sense of, okay, this is the height of the shell. This entire length here, that is the height of the shell. So we measure that length, or that height, if you will, the same way we've always measured, the right minus the left. So we have to take the right, which is 4, subtract off the left, which is the square root of x. But then we say, well, I need everything in terms of y, so I don't want to look at y equals the square root of x. I want to look at x equals to y squared. Sorry. So the right function is, or sorry, right function is 4. The left function is y squared. Therefore, the height is 4 minus y squared. So maybe just take the most trivial case of a shell, and that is this shell laying on the axis or the base of that region. We know for sure that that is a length of 4, right? Because it just runs from 0 to 4. But then the problem is that any other shell that I draw in here, now they're all varied. They all have different heights. Okay. Does that make sense? I don't know. The pictures were lifesavers for me when I first learned this stuff. Okay. So that's our h. And then the radius is always just the distance from your cross-section or your rectangle to the perpendicular to the axis of revolution. So that is my radius. And it's just measured by, this value here, which is a y value. So that's y5, this is y1, whatever. So the radius is y. Okay, that color doesn't show up very well. The radius is y. Okay. So since we're looking at the shell method, we're hopefully writing down or thinking 2 pi RH. So 2 pi times R times H dy. And then we've got to figure out the bottom limit, pretty straightforward, y equals 0. And we got to figure out where the top limit of integration is. So what is that? 2. So y ranges from 0 to 2. That's the appropriate setup. If you just had y times y squared, it's true that the function is y squared, but we're not measuring function values. We're measuring the difference, or the length from here to here, which is the difference 4 minus y squared. Otherwise, you don't get a shell. So you're doing something different. Now, it's important to realize that you cannot integrate across a product like this. So whenever you see a product, until we get to chapter 8, which is the next unit we look at, you won't be able to integrate products unless it's like a simple U substitution. Okay. So I would just recommend here multiplying this out. So multiply and expand all of this stuff. Or sorry, multiply and combine. And that way you're just integrating powers of y. So anyhow, this should come out to be 8 pi. Any questions? And don't write r squared either. The r squared showed up when we're computing the disk or washer method, because we had those cross sections as circles or washers. So it's just 2 pi times the radius times the height for the shell method. Everybody good? Questions on that? Move it forward. Yeah, I really just had these pieces of paper so you could kind of, I don't know, I think it makes a little more sense with the shell because you have it like this, and if you roll it together, you know, so here's your rectangle, right? And I'm going to rotate it parallel to the axis of revolution. I can see that's like a cylindrical shell, right? Versus my rectangle rotating it perpendicular, I just get a circle. So I just had those there for that purpose. But let's go ahead and summarize these two since they're both listed here. Shells, if you want to take these pages off and just reference as a quick reference, shells are parallel to the axis of revolution. The cross-sectional areas are 2 times pi times r times h. And we got two things here. Let's see, if we're doing the height in terms of y, the height is always measured by the right minus the left. Or if we have them running in the x direction, the height is measured by the top minus the bottom. Top minus bottom for integrating with respect to x. Let's just go ahead and note here that the radius r is and we'll just generalize. In a lot of examples, if it's butted up against the axis, then the radius is either x or y. But the radius changes depending on what axis you rotate it around. As long as you're always rotating it around the x or the y axis, r for the shells will be x or y. But the radius changes once we start rotating it around a different axis. So we'll just say r is the distance from each shell to the axis of revolution. So those always, when we're measuring the radius, I think maybe we should think about it as the perpendicular distance. Just like in that last example, our cross-section was like this, but we're rotating it around the x-axis. So this right here was our radius, perpendicular to the shells, if that makes sense. Okay. So you can, maybe that's helpful. You can detach that if you need to. And then our shells, disc washers, rather. Perpendicular to the axis of revolution. So in general, we had the area was pi times the large radius squared minus the small radius squared. That's capital R. All right. We got a couple more examples here. This example here is intended to show that, well, let's see, what are we doing? So the next two, rather. So we're going to take the same region, y equals x and y equals x to the 1/3 in the first quadrant, and revolve that around the x-axis and use the shell method to find the volume. And then in example 4, we can look at the same region and revolve it about the x-axis, use the disk washer method to determine the volume. And since it's the same region rotated around the same axis, the volume shouldn't change. And what we'll see is that both methods give you the same exact volume. So the question is, like after you see this, is it's, maybe why do we have these two methods to find the volume? And or which one should I use? Or does it matter? Something to that effect. So the cube root x to the 1/3, remember that was that kind of funky S shape? Sort of flat here at the origin and does that. And then y equals to x. In the first quadrant revolved about the x-axis. And we're going to use the shell method. So we want our shells parallel to our axis of revolution. So that's, again, 2 pi times r times h. So what's the height of my shell? Height is the right function minus the left. So my right function is, and my left function is what? Okay, so remember though, we want to do everything with respect to y. So the right function is y, and the left function is y cubed. Radius is the perpendicular distance to the axis of revolution from your shell, perpendicular to the axis of revolution. That distance measured by r. But again, we're rotating it around the x-axis, so everything matches up with our y values here. So this radius for each shell, no matter where we drew that, just y. So we're thinking about this as some y value minus 0. Y minus 0. Okay. And then so that we have our volume as 2 pi times the integral of our radius times our height. With respect to y. Y ranges from 0 to where? To 1. Is everyone sure about that?
Yes.
Okay. All right. So kind of similar to our last problem, you want to multiply that stuff through. I guess we can check, since we're asked to check, let's run through this real quick. I'll simplify this stuff down here. Y squared minus y to the 4th. So our antiderivative is y cubed. Oops, I need to leave some space. So we have 2 pi times y cubed over 3 minus y to the 5th over 5. Evaluated from 0 to 1. So that's 2 pi times a 3rd minus a 5th. And what that'll give us is 4 pi over 15. Okay, So, same region, same quadrant, revolved around the same axis. You're generating the same volume, but this time we're going to use the disk washer method to compute that volume. So disks, washers. Well, are we going to have a disk or a washer? So washer, because we have a gap between our region and the axis of revolution. Okay, so that's a thickness of dx. We need everything in terms of x. Fold around the x-axis. Sorry, that's an arrow. Okay, so we see that there's a gap there that we're going to be using a washer, which is pi times outer radius squared minus inner radius squared. Okay, what's my outer radius? Is that distance there? So that's x to the 1/3. That's outer radius, and then my inner radius is the distance from the bottom function to the axis of revolution. So that's just x. All right. Anybody have any questions on that? Yeah. Up here, this one? So we could, since they're y values, we could either find the intersections in terms of x and then just plug back in for one of those functions. So we could, what we're asking is when does, for instance, when does this graph intersect this graph in the first quadrant? And so we'll cube both sides, right? So you have when does x cubed equal to x? And then really that's when does x cubed minus x equals 0, and then we factor that. Like that. So we know it's not -1 because we're in the first quadrant, so. And if we needed our y values, again, we have the relationship between, a pretty easy relationship between x and y for one of those equations we plug into. So if x is 1 here, y is 1 here. Any other questions? All right, so let's just put this into our volume is pi times the integral outer radius squared minus the inner radius squared with respect to x. So that's outer radius 1/3, inner radius was, sorry, x to the 1/3, inner radius was x. From above, we know those those points are 0, 0, and 1, 1. It looks totally different. It's still, both of these are still measuring the same volume. It's different methods. So here we have pi times the integral x to the 2/3 minus x squared. So that's antiderivative of x to the 2/3 is x to the 5/3 times 3/5 minus x cubed over 3. So the bounds are really simple. We have just pi times 3/5 minus 1/3. Which is also 4 pi over 15. really haven't seen a reason for using one or the other, but what would be the advantage of using one over the other? Why would it, in other words, why is it advantageous to have two different ways to do the same thing?
One might be easier than the other one, or less complicated.
Yeah. Right, one might be less complicated than the other. And we kind of saw that with, like, you know, I forget what section it was in. Maybe it was in 6.2, where it said, well, do we want to integrate the inverse sine, or do we want to solve the other equation and just integrate sine of x instead of the inverse sine of x? So depending on what function you're dealing with, always bearing in mind that whether you're using the washer or the shell method, you're going to have to integrate that thing. So whenever you set that up and you see something like inverse sine or you know, like a logarithm maybe, you might want to look at the other method, because if one of them's with respect to x, then the other one's going to be with respect to y. So maybe I can't integrate in terms of x, but if I solved everything the other way, I can integrate pretty easily with respect to y. And either method, as we've seen, will give you a volume. So we've got three more. The last two examples are the ones where we revolve around a different axis. So let's use the shell method to find the volume of a solid formed when a hole of radius 2 is drilled symmetrically along the axis of a right circular cylinder, height 6, radius 4. The one in your homework is they want you to find the volume. They want you to find the volume of a right circular cone that you've drilled a hole through. So this is kind of similar to that one. So what would be the volume of this cone if I drilled a hole through it? Naturally, it wouldn't look like that, but. So you've got this hole here. Whatever that is. It's kind of along this in the same vein of that problem in your homework. So again, we don't want to think about the figure that is the three-dimensional figure. We don't want to think about that. We want to think about what can I revolve around an axis that will give me that three-dimensional figure. That's what we want to think about. So if I'm looking at a right circular cone, let's just draw this out. Assuming that I can. Might as well make things simple. Center it at the origin. So what would I have to rotate? This is our right circular cone. We'll worry about the hole in a minute. What would I have to rotate around an axis to get that?
You could rotate x equals 4 around the y-axis.
So a line, if we take that line and rotate it around, would that sweep out a cylinder?
Obviously, you have to bound 6.
Yeah, so okay, a line at 4 with a height of 6. But again, if I take this line and I rotate it around an axis, is that going to give me a filled-in cylinder? No. So that would be hollow. We want all of this. We'll worry about the hole in a minute. But we want all of this to be filled in. Oh, I thought that moved. So a line isn't totally accurate. It's on the right track though.
Start the line. X equals 0 also.
Yeah. So what would that be? What would that look like? If I said this line here to this line here, bound by this line here, a rectangle. Yeah. So if I take that rectangle and I rotate it around the y-axis, then I've swept out this right circular cylinder. Okay. So then how do we account for the hole that's drilled in here?
Y equals 0. 2 different ones.
Yeah, to a different one. So what would it can't be 0 because then that fills in the whole thing. So how do we account for the hole? X equals 2 because we're drilling a hole of radius 2 through here, right? So there's, well, I should have left that. We want a hole here of radius 2. So we actually want to take this with a radius equal to 2, deleted from that. So really what that equates to is taking this rectangle that's from 2 to 4 with a height of 6 and rotating that around the y-axis. Let me draw that again. It looks like it reminds me of Shel Silverstein's drawing. Anybody know who that is? Light in the Attic? Yeah. Okay. For a second, sometimes I think my references are dated just because I'm old and I don't pay attention to the same thing other people pay attention to, but it's good to know y'all know who he is. All right, so then this is the figure here that we're rotating around the y-axis, and that's going to give us our right circular cylinder with a hole drilled through it. The one in your homework, like I said, is similar. It's a little bit harder because you're not just simply rotating a rectangle around the y-axis. Yeah, it's a little bit more involved. I think that's all I'll say about it. So, would it be easier to do the washers here or to do the shells? Washers? Washers are perpendicular to our axis of revolution. This is dy. So what would that look like if we're computing the volume of this using the washer method with respect to y? So I want to take a shot at that. Yeah.
Integrated from 0 to 6, 4 squared minus 2 squared.
Okay. What do y'all think?
Yes.
Yeah, except for we're missing the pi. Yep. Other than that, y'all agree? Right minus the left. Sorry, not right minus the left. Outer radius, capital R, minus the inner radius, lowercase r, squared. So it's pretty easy to integrate. It's just a constant. What do we have? 16 minus 4. So we have pi times the integral from 0 to 6 of 12 dy. That's pi times 12y evaluated from 0 to 6. And that's 12 times 6, that's 72 pi. If you did this the shell method, using the shells, you would get the same answer. It's the same volume. Or rather, the volume doesn't change regardless of what method we use. Okay. Questions on that?
So you said use the shell method. Do you not want us to?
Oh, it did say use the shell method. See, I lose points for not reading the question. Oh yeah, so it's first word, almost. Okay, so let's redo that. I mean, we don't have to redo it, but I don't know if I can fit this in here. What was that, number 5? Let me go down here. It's just as easy with the shell method, so I don't anticipate there's going to be issues with it. But we had this from 2 to 4, 6. Rotated around the y-axis, our shells are parallel. So dx bounds are from 2 to 4 on the x, and then it's 2 pi. So I'll put that here 2 pi times the height. The height is always 6 times the radius. Distance from here to here is the radius. And that's just some x value. To 6, we're integrating 6x dx times 2 pi from 2 to 4. Sorry, we should specify that this is number 5 using the shell. I'll leave that for you to verify if you want, but that's also 72 pi. All right. Questions about that example? All right, let's take a break and then we'll look at the last 2 examples where we're revolving around a different axis.
The bottom is closed.
So when we take these regions, I don't believe we saw this in 6.3. We were always rotating those around the x or the y axis. When we take these regions and revolve them around different lines, like x equals to -2, let's see what happens to our, see what changes rather. So we have x squared, x equals to 1, y equals to 0. So that's our region. We're going to use the shell method to find the volume revolved about the line x equals to -2. We're thinking that we need to find 2 pi RH, the radius and height of the shell revolved around x equal -2. Again, shell, all of our shells are parallel to the axis of revolution. So we're integrating with respect to x. So the way we measure the height, does that change? The height of each shell here still measured by the top minus the bottom. So height, still the top minus the bottom, which is x squared minus 0, or just x squared. But the radius does change, because now the radius, perpendicular distance from the shell to the axis of revolution. So what is the radius here? X plus 2, do y'all agree? It's x plus 2. If we're measuring the length of this horizontal piece right here, then it's just the right minus the left. Right minus left. This is some x value, and this is -2. So it's right minus left. So our radius is just x plus 2. So that's what's going to change when you rotate these about, the shell method about a different axis. Your radius will change.
If you're rotating something, like if that was x plus like 3, instead of x equals -2, if it was x equals 3?
Uh-huh.
Would it be left minus right?
No, it would still be right minus left. So like if we were rotating it around x equals to 3, it's still the right minus the left. So we had that region rotated around this axis, and that was our shell. This is our radius. Sorry, this is x equals to 3. So it's 3 minus x.
Okay.
So just think right minus left because it's a horizontal element or dimension. Does that make sense? Any questions? So then our volume becomes 2 pi times r times h. And then the bounds on x go from 0 to 1. That's the setup. You distribute that x squared, you're still integrating just powers of x. So you should come out, if you're working these, that's 11 pi over 6. Anyone have any questions on that? The next example's very similar.
So would there not be anything to the left of the y-axis? Is it the graph for x squared right?
Yeah, so our x squared is really like this, right? But it says find the region bound by x squared, x equal 1 and y equals 0. So if we drew this, here's our x squared, here's y equals 0, and here's x equals to 1. It's only this region that's bound. That one's not bound by anything, so we don't consider that piece. Any other questions about that? I do see that, it's pretty common on the exam for people to draw the correct graphs and such, but then they misidentify what region is actually enclosed by the function and the line or whatever it is. So, as you're working through your homework, you'll know whether or not you're getting those regions correct. So we talked about this. Just someone had a question on this earlier. The function was the square root of sine x. And so the square root of sine x looks like this. It keeps going in all directions like that. But then I think it was what, y and the line y equals to 1, which is here. These peaks. So we have the region bound by the function, the line, and x equals to 0. So we're looking at x equals to 0, the line y equals to 1, and what's bound by the curve root sine x. So it's this area that we're finding the volume of. I assume that was from a volume section. So all of this stuff we don't even pay attention to. So we probably should similar to our last problem, if you want to attempt this and check that you get 17 pi over 15, but we'll skip that for now. All right, so we've seen volumes, integrals can represent volumes. Now we'll look at how we can calculate an arc length. In other words, the length of a curve. So if I gave you this function from A to B, and I ask what's the length of that curve, that's what we're looking at, is the length of that arc. So that's how we explicitly represent a curve, kind of how we're accustomed to seeing that. You might remember from implicit differentiation that we can represent curves implicitly, and that's where we got all those weird, like infinities. It's like in shape of an infinity, or flowers, or all those weird things were implicitly defined curves. And we can define curves parametrically, which we'll talk about in chapter 12. And these can, I don't know, whatever, they can vary. That's good enough. So what's the length of that parametrically defined curve? We'll look at that in chapter 12 as well. Okay, so the idea, sine x from 0 to pi, we're just going to use this to sort of motivate where the formula comes from. At any point, I never expect you to justify where these things come from. If we have the capabilities to show where they come from, then I'll try to show some of these things, just so we're not just looking at a formula and wondering how that came about. Okay, so let's say that's sine from 0 to pi. And we wanted to know what is the length of that curve. It's kind of, you kind of see it there below what's happening. 649. I think this is. Changed. That's the right one. And so what we'll do is we'll approximate it. Clearly that's a terrible approximation, but we're going to use these line segments and simply do this. So what we're seeing unfold in this slider right here, what are we actually doing? The what? Yeah, so well, we're not measuring the slopes of the lines, right? We're measuring the lengths of the lines. But we see as we put more and more lines in there, we get a better and better approximation of the curve, the length of the curve, right? So that process is the same as the process we've looked at since we started talking about area in Calc 1. Let the number of line segments approach infinity. We're going to sum all of those up. Infinite sum like that turns into a definite integral. So that's the idea. Just to take, I don't know the length of that curve, but what if I knew the length of this thing? That looks pretty straight. So I want to measure, I don't know, just call that length 1. I want to measure that length, and then I want to measure length 2, and et cetera, et cetera, et cetera. And the way we're going to look at that is how they kind of have structured here. here's length 1, our base of the right triangle that we've created is just some change in the x value, so we'll call it delta x, and the change in the y value is delta y. So I don't know that I'll put all of the notation together, but that's the idea. We're going to sum all of this stuff up to infinity, and that's going to turn into a integral for us. All right, so this is our length 1. So we want it, that's what we're trying to measure, length 1 from delta x1 and delta y1. And then so to measure that length, we'll just use the Pythagorean theorem and say that L1 is the square root of delta x1 squared plus delta y1 squared. But that's not really helpful, because if we have this function, how are we going to measure these infinitesimally small changes in x and y when there's infinitely many of them, right? So we've got to take this and sort of manipulate this into something that makes sense. I mean, this makes sense, but it's not, we can't work with it as it is. Okay, did I start that? Okay. So what we're going to do is inside the radical, we're going to factor out a delta x squared from both terms. So we're going to take delta x1 squared out of delta x1 squared and delta y1 squared. So what is that going to leave us with after we factor that out? 1 plus delta y1 squared over delta x1 squared. So really two things happen when we do that. We have the square root of delta x1 squared, so that can come out of the radical. As just delta x1. And let's rewrite our expression as just a quantity squared. So we'll have delta y1 over delta x1 quantity squared. As the length. Yeah. Yeah, plus or minus here, right? In the context of what we're doing, we're dealing with a length, so we're only going to consider the positive root. Yeah, valid question though. Normally we deal with plus minus. All right, and then we'll go to page 2 to see how we're going to handle this thing here. How we're handling the delta y over delta x. We have to remember something from Calc 1. So yeah, it's not in here. That's unfortunate. Let me grab this. This theorem. But the theorem relates the slope. What we're looking at there is just a change in y over a change in x that's being squared. So we're looking at a slope of a line with our delta x over delta y. So do y'all remember the mean value theorem? Does that ring a bell at all?
Yes.
So the mean value theorem says that if we have some continuous function on the closed interval and differentiable on the open interval, meaning just the derivative exists at every value on that interval, then there is at least one x value, we're going to call it c, in between our a and b, so somewhere inside that interval, where f of b minus f of a over b minus a is f prime of c. So how do we interpret this right here? What is that? Is it what? Average rate of change, which is just the slope between those 2 points, right? So here's, for all intents and purposes, for us, this is basically a version of our slope that we have under the radical that's being squared. So that's just a slope. So what it says is somewhere inside those two endpoints, we closed it off, somewhere inside there, the slope of that particular line, which is resembled here, at some value x is equal to the derivative at that particular value. Okay, so we could write this. We're just gonna we use x instead of c. That's no big deal. Okay. There's sort of a visual validation of that as well. So from the previous page, we had L1 was delta x1 times the square root of 1 plus delta y1 over delta x1, and then that was squared. So slope squared, according to the mean value theorem, our function is continuous on some interval, and the derivative exists, then we're simply going to call this delta y over delta x f prime, because according to the mean value theorem, somewhere it is the same thing. So, view this as our L1. This is the L1 that we're measuring. Here's our delta x or delta y. We're saying some x value in here, visually we can see some x value in here, this one in particular, is where this slope is the same thing as my derivative at that point. So that's how we kind of work this function in here. We have then L1 is delta x times the square root of 1 plus f prime squared by the mean value theorem. I know we sort of didn't mention some of the technical aspects, like it's continuous and differentiable, but that's the main idea.
You drop the delta x1.
Yeah, yeah. So we would say that this is
Before that, like before the square.
Where this step
No, down.
down.
You just drop the delta x.
Yeah, I should be a little bit more precise. We'll call that f prime at x sub 1.
I was talking at like the left of west. Right
He's
after.
saying you forgot
Oh,
the
yeah, I see.
Yeah.
I didn't know if
Yeah.
that mattered. So,
Yeah, we should be precise. So that's the length of that first hypotenuse, if you will. The length of all the other hypotenuses would be the same. And then so we take all of that stuff and we sum it up. Sum from k equals 1 to n of L sub k. That gives us our, what do we call this, arc length. And then we, of course, to make it exact, we have to let n approach infinity. Okay. So we're just going to put this expression in for L that we have here. Do I have that formula? Okay, so it's on the next page. Definition of the arc length. There's our infinite sum from a to b, and then we have the square root of 1 plus the derivative squared. So make sure that you're reading that notation correctly. That's the first derivative, then squared. That's not x squared, or I don't know, however we might misinterpret that. It's f prime of x squared. So I mean, there is tendency for confusion because we are finding an antiderivative here, but we're also having to compute derivatives as well. So, you know, stay organized, otherwise you're mixing derivatives and antiderivatives. And then so we can go back to that, that first one that we used to motivate this. What's the arc length of sine x from 0 to pi? We'll set this one up only because the integral is not something we can do. So we'll just set it up. But really what it boils down to is finding the first derivative and squaring it and just putting in that into the integrand. So I would just recommend starting out just finding the derivative. The derivative of y equals sine x is what? Yeah. So the derivative is cosine x. And then we'll take the derivative and square that. I'm just thinking about what's under the radical. We can put it all together if we need to. Then we add 1. So that's cosine squared plus 1. And then that's the expression we're going to put underneath that radical for the arc length formula. So you just have to remember the arc length formula. In computing the arc length, then I need to say that it's the integral from, I'm given that from 0 to pi. And it's the square root of 1 plus my derivative squared. However you want to write that. With respect to x. So that's the setup to compute the arc length. Yeah. Not quite. Otherwise we could integrate it. But remember, it's cosine squared plus sine squared equals 1. So like sine squared is 1 minus cosine squared. So yeah, that's actually a difficult integral to do. But yeah, so we just set it up. Example 2 we can compute. What we look at in the next section is sort of related to what we're doing here, because we do need the arc length to compute surface areas, and that's what we look at in 6.6. So I don't know, you get, with arc length, you kind of get a twofer. Find the arc length of 2/3 x to the 3/2 between 3 and 8. So it always has to specify, right? If we have to stop somewhere, otherwise the answer is infinity. So those are our bounds from 3 to 8. And we just need to figure out what we're inserting under the radical. So I don't know, this is just normally how I do it, just so I can kind of keep track of what I'm dealing with. Okay, so we have the derivative of y would give us what? Root x, square root of x, x to the 1/2, whatever. Right. 3/2 comes out to multiply the 2/3. Remember, we're taking the derivative. 3/2 comes out, multiplies 2/3. We take 1 away from the power. 3/2 minus 2/2 is 1/2. So if y prime is x to the 1/2, so much to have enough space. 2, we're going to take y prime and then square that, which gives us x. Then we're going to add 1. is x plus 1, and then that's what's going under the radical. So arc length, integral from 3 to 8, the square root of that expression we had after step 3, square root of x plus 1 dx. That's it. When we compute that, we have the length of that curve. So what are we using here to evaluate this antiderivative?
Use substitution.
A u substitution can work. You may not need a u substitution. Again, we've got this linear argument. But anyhow, let's let u equal to x plus 1 du is dx. So we have the integral of u to the 1/2, the square root of u, times du. If our lower limit is 3 on x, then our lower limit is 4 for u. Upper limit is 8 for x. Upper limit is 9 for u. So that's not too bad. Find the antiderivative of u to the 1/2. So we add 2 over 2, u to the 3/2 divided by 3/2 or times 2/3. Evaluated from 4 to 9. So it really just depends on the instructions at this point. If they want an exact answer, then you leave it exact. Otherwise, we could figure out what the exact answer is and type it in our calculator. So I'm going to leave this 2/3 out. 9 to the 3/2 minus 4 to the 3/2. So how do we leave 9 to the 3/2 exact? Simplify that though. What is 9 to the 3/2? Square root is, say that again?
Square root of 9 cubed.
Square root of 9 cubed. Can we simplify the square root of 9 cubed? Yeah. In fact, anything to the 3/2 is actually, we can actually simplify that. So there's the square root of n cubed. Since we got 2 of those, we can pull that out. So some number to the 3/2, assuming it's 0 or positive, is just n times the square root of n. So what is this going to be?
27.
9 to the 3/2, right? It's 9 times the square root of 9, or 9 times 3, which is 27. This is 4 times the square root of 4, which is 8. So we have the 2/3 times 27 minus, what was it, 8? Whatever that is, 38 over 3 is what that is exactly. Okay. Anybody have any questions? Yeah.
I'm still kind of lost on why you're adding 1 in for the third step.
Part of the formula. Yeah, the arc length is the square root of 1 plus the derivative squared.
Okay.
Yeah. So that 1 was just a result of factoring out that delta x.
Oh, okay.
Delta x squared, rather, under the radical. So yeah, it's that 1 plus the f prime squared built into the formula. Okay. We can also do this with respect to y. You note the similar pattern here. Some function of y derivative squared. So we can look at that here in example 3. This example is a little bit more involved because fortunately for us when we're finding these types of integrals, generally these more complicated ones where we don't have a U substitution approach, these more complicated functions will always work out for us to be a perfect square, meaning the 1 plus derivative squared part will come out to be a perfect square, so you can take the square root of it. Otherwise, if it's something a little bit more difficult than like x plus 1 under the radical, we don't have the tools to integrate that yet. So with that in mind, you should, when you're working these, if you get something funky under the radical and it doesn't go away, you should check your work, because you should get a perfect square with more complex expressions. So let's, I don't know how you like to look at these. I'm going to look at this as 1/4 times y to the 4th plus, because I don't have to take the derivative of this, 1/8 times y to the negative 2. So just in preparation to take the derivative. So 1 x prime derivative with respect to y. Okay. So what's our derivative? Y to the third, first term, minus 1/4 y to the negative 3, right? So now we've got to take that and square it. So we're going to take x prime and square it. So we have, I'll just write this out explicitly and then we can look at it squared. So there's x prime, we're going to square that. And there is a simple way to know if we're dealing with perfect squares, and we'll look at that. But there we have the first thing squared, the last thing squared, and then twice the product of the two terms. So when we multiply the y to the negative 3 by the y to the third, that's just y to the 0, which is 1. And then we have negative 1/4. So we have twice that product. It gives us negative 1/2. So that is our derivative squared. And then we need to add 1 to all of that. And so when we add 1 to all of that, just combining like terms, we have still y to the 6th. We have now a positive 1/2, 1 minus a half. And then we have our positive 16th y to the negative 6. So then we're looking at that and guessing or trying to determine, well, now, is that a perfect square? Because I know I have to take the square root of all of that stuff. So hopefully that's a perfect square. Don't just assume it is. There's a really easy way to tell. But that's where we're going. Anybody have any questions on what we've done? I know it's been a while since some of you have done derivatives. But here they are, so you might want to have to look over that again. Okay, so the way we can look at this is, what we started with squaring was essentially we had a minus b, and we squared that to get a squared plus b squared minus 2ab, right? Minus twice their product. That's the formula for that. The other perfect square in that sense that we have is a plus b quantity squared, which is simply a squared plus b squared plus 2ab. So what we notice here is when we look at, and I'll end up erasing this, But when we look at this, that's our a squared. Did that change when we added 1? No, that's still a squared. This is our b squared. Did that change? From here to here? No, it's still the same thing. Notice the difference here in the middle terms. This is a positive 2ab. This is a negative 2ab. Don't we have that? This was a negative 1/2. This is a positive 1/2. These two things, by the difference, how can I say that? The square of a difference versus the square of a sum is just in this middle term right here. 2ab and 2ab are the same number. They're just opposite in sign. That's really what all you're looking for. Is that middle number the same as what it was, just opposite in sign? And if it is, I know that what I had up here in blue came directly from this thing minus this thing squared. This is a negative 1/2. What I got when I added 1 now, positive 1/2, right? So then I can say, well, this is a perfect square. It's not y cubed minus 1/4 y to the negative 3. It's y cubed plus 1/4 y to the negative 3. Does that make sense? I think that's the most efficient way to tell if you're dealing with the perfect square and how it would factor. Okay. So can I get rid of that red and blue stuff? I mean, I guess I could leave this just so we can remember. But this thing, let's work with it down here, is just y cubed plus 1/4 y to the negative 3 squared, which is great because again we have to put that underneath the radical in order to compute the arc length. So we've got a quantity squared that we're taking the square root of. So the arc length integral from a y ranges from 1 to 2 that was given. So from 1 to 2. And I'll just write all this in here so we can not miss a step. All right. So if that wasn't a square, like I said, then you're looking at that expression under the radical, and you're saying, well, how the heck do I even integrate that? Like, u substitution doesn't work. That's all I've got, right? U substitution doesn't work. How do I integrate that? You've probably done something wrong. So then at some point you would go back up through here and say, did I miss the fact that this is a perfect square? Yeah, I did. So now it's a perfect square. Now we can actually work with finding the antiderivative. So we can work that out pretty straightforward now, just integrating powers of y. Let's take a look. This is going to be y to the 4th over 4 plus our 1/4 times antiderivative of y to the negative 3 would give us what? Yeah, so we have y to the negative 2 power divided by negative 2. We'll combine that with the positive 1/4. So what I would do is, since both of them have a 1/4, I would just take that out and not deal with that until after the fact. So we have y to the 4th here. We have minus 1/2 y to the negative 2 from 1 to 2. So we'll just write our answer as an exact value. 123
over 32.
Do y'all have any questions on that? So don't assume that they're gonna be perfect squares, like, actually work through it. So here's one to work through. So let's see what we can do in 10 minutes. Take 10 minutes and compute this arc length.
Is it 117?
That one?
120.
Oh yeah, 123.
That's subtract. I have half, and this is on a plus one. How did you work that? Take out that first.
But, so what you have is you're not accounting for the 2 and the 1/4. So if you square this, it's so you use 16. So basically, fix the squares. Well, if we look at it backwards, these perfect squares are not.
So for this one, it would just be 116.
No, that would be, so you came from here, right? So you're gonna look at it like, all right, well, this is, let's look at this one. This is, this is our a squared. So when we write this here, we want to know what is that, a minus b or a plus b, whatever. We want to know what a is, but what we have here is a squared.
So you have to take this. So it's 1/2.
Yeah.
Yeah.
Yes.
That's
So it converts into here. That makes sense? That makes sense.
Y equals 2.
So I took it to subtracted y.
2 minus So this is your radius, 2 minus y, but this is your height. So your height is 1 minus.
Yeah, that's possible.
It's 2 AB, right? Yes, and then it should be this, right? Because it would be this. It would be squared over square root. So you would take and then because I got your oh, I was just straight up plugging it into the I did that. I was plugging it into the integrator. I wouldn't actually. I was like so confused. I was like, this can't be 0. Like that makes no sense.
that's the right. Yeah, sorry.
Just checking.
Yeah, well, this actually literally, like the square root of 1 plus the.
It's pretty crazy.
Yeah.
Yeah, it's like one of those cases where like somebody
This looks okay.
is like
This
a
estimate doesn't
brand.
actually got 1. But remember, we have to square root of that, so you want
I
to
got
try to
3.
factor this into a perfect square.
Because I think it's supposed to plus 1 half. Maybe I'm crazy. Because this becomes hopefully most of the problems are like this are always or
They have.
yeah, because like otherwise it's so awful to like actually like sort it out. Because I was like looking at this and I was like, yeah, this has to be squared. There's no way to do this.
It was like negative.
Yeah, when you were saying the negatives, that's what you change what happens. I had to like think like I still have to logically test the story after that. So if you use the negative, so what was your mistake? What is negative?
So, here though, with any like that, you kind of say that.
Because you have to.
And then say this is usually, but then we square that.
Yeah.
Line like so.
What is negative line? So this means when divided by line.
So I expanded it out.
Let's just take the actual.
So you just have to take it down.
Oh, I see. Like it's like the X or not power rule, but I know what you're talking about. It's like an exponent rule, right? What is it? This is what you're talking about earlier. Line 2 power rule.
It's not true.
Oh wait, oh this is funny.
Add exponent out here.
Because you fill the check. So this doesn't work because there's no E, right? Because I'm pretty sure the laws only let the next block.
Actually, that is incorrect.
Wait, let me read
This is like all through, but it looks sound.
This is equal to negative x.
I don't get if I'm asking. I just know that.
We had this one.
Yep.
It's like, pull out 120.
This one's negative.
Wait, so where is it wrong?
Actually, just a lack of so this.
Used to be.
It's like the
These problems are actually kind of nice.
6 years ago, I was
I don't know.
I don't know. Because they don't allow you to use graphic.
It's just integrated with this one.
First thing square.
Felt like, I don't know. You're just gonna square it.
Start everything.
Excel? Excel has a function to track the complex numbers. I'm pretty random that I know that. But like, yeah, it's like for Excel too. Like, what like Excel mostly is? Yeah, like what data? Because most of the Excel are like that's the time like working.
Was that when you had to manage the square?
But the last 3 years, it's
No, it's twice their product.
I don't even like want to. Because
no,
mine is
the
very big.
last.
Oh, this one?
Yeah.
Oh,
So should it be?
Could be negative. Can you rewrite that? Negative 1 to the power of 2 now. And does that way when you bring down that one?
How do I back and forth because
Oh, this just doing that for fun?
I was like, how do I take the negative? The negative. Wait, oh.
It's like that. Where it's like one is like it's like another one.
Well, that's because it was negative.
Wait,
I think that's why. Maybe I thought, right? How'd I get the right answer?
They're actually.
It's like it's a whole book about like well, wasn't Newton like really like spurred? Like he was like I'm pretty sure he was like a hermit and he like found like all this stuff and like he didn't like really release it until oh, but he also did these too. I think there was a crash that like he did like hella he did. Oh my god, I'm pretty sure he did philosophy too. Because I'm reading about it in my logic class. He like straight up like did something. Leibniz was insane.
All right, we have a minute left. I have enough time to write down the answer if you want to try to verify. And then we'll look at this next class. All right. Have a good break.
Thank you.